Good time of the day, everyone. This is Ivan from JePPIX, the European Photonic Industry Consortium. And today we continue our series of the online technology meetings with a very exciting topic of hybrid photonic integration. And this event will be supported by JePPIX and our member PICs. And the agenda of today's event, you can see now in front of you. We'll start with a keynote presentation by Professor Kevin Williams, presenting JePPIX and the Eindhoven University of Technology. We'll then switch to the presentation by Thales on the applications of microtransfer printed 3.5 on silicon nitride for microwave photonics and sensing by Vincent Billault, the research engineer in Thales. And then the talk of smart photonics about putting the light into your chips and heterogeneous integration of indium phosphide photonics, presented by Alonso Millan-Mejia, senior scientist and the process architect. The next talk will be done by VPI Photonics, and Andrzej Polatynski will present single design and multiple fabs, modeling and design strategies for hybrid PICs. Unfortunately, the talk after this, presented by Ficantect, is cancelled. So we'll follow up with Vanguard automation, the next generation photonic integration and packaging solutions with photonic wire bonding and facet-attached micro-optical elements, presented by the CEO of Vanguard Automation, Thorsten. And last but not the least, the presentation of X-celeprint on the microtransfer printed for printing for integrated photonics, presented by Ruggero, the supply chain scientist. I would also like to mention that this event is done in partnership with JePPIX, the joint European pilot line for indium phosphide integrated photonics, and sponsored by PICs. And without further delay, I'd like to present to you the first speaker of today that actually represents our partner JePPIX, Professor Kevin Williams. Please, Kevin, whenever you're ready, you could start your presentation. The floor is yours.
Very much. So, thank you. I hope you can see the title slide on hybrid photonic integration. And a colleague from JePPIX will tell me otherwise if it's not displaying. Real pleasure to be talking to you this afternoon and see so many on this call. JePPIX, of course, is an open platform, so I'd particularly like to share with you our approach to open access development opportunities and the vision going forwards with foundry-sourced components and technologies. JePPIX is the joint European platform for photonic integration, for components, for circuits, and we have the mission to bring together the European PIC supply chain and the developers that benefit from this supply chain. And of course, most recently, we've been really looking at driving the industrialization with the pilot line initiatives for high performance PIC technologies. So over the last decades, we've been looking at MPW services that many people will be familiar with for low-cost PIC prototyping, for orientating with the supply chain. But more recently, we've been scaling up, looking at the pilot line services that bridge that gap from prototype through to production. And of course, we have the training services now scaled up for industry professionals as well. And the technology we focus on, it's premium in terms of performance, but also affordable. For the indium phosphide technologies, you have the advantage of the native active building blocks, the powerful process design kits, the high-speed components. We've now been demonstrating up to 100 gigahertz for some of the components. And the silicon nitride, the ultra-low waveguide losses, the low loss coupling into the fibers. And so far, this has all been very much available through prototyping as individual technologies, through MPW runs. Now we're scaling to pilot production with pre-qualified processes enabling manufacturable designs. And in parallel to that, with other partners, looking at engagement models, co-financing models for new entrants to the PIC industry. To give you some examples of how we're now bringing this together, partners such as PICs, such as Lion-X, have been looking at integrating these individual elements, the silicon nitride circuits with indium phosphide or gallium arsenide circuits. Here's a recent example where you get very high performance by combining the active materials from 3-5 semiconductors and the dielectrics with very, very low loss, getting the line widths down without compromising on side mode suppression ratio, getting the powers up, getting tunability that would otherwise be quite challenging. And this is really just the starting point. As we master these technologies and master the hybrid integration, we will drive performance further. In the research programs, we've been looking at electronic integration with photonic circuits. So the left example there, you're seeing a full wafer of bi-CMOS electronics and a membrane on top of that of indium phosphide circuits with lasers, with receivers, with arrayed waveguides. So you've got the building blocks coming together there for drivers, for electronics. You've got all the components you might need for sensor technologies and transceiver technologies. And that's helping us to drive up the speed and drive down the energy needs. In the middle, we've got the nanophotonic programs. This at the moment is an academic activity, but it's available now as an MPW prototyping service through JePPIX. So here you've got all the functional components you would hope for from indium phosphide, lasers, amplifiers, and detectors, UTC detectors. And you've also got that nanophotonic platform that includes slot technology, ring resonators, surface grating couplers. So a very powerful combination of the nanophotonic as well as the actives. And on the right, it gives you an idea of where we see the industry going as we move towards three-dimensional integration with layers of photonics, electronics, and perhaps MEMS technologies and other sensor technologies. One of the technologies we see as being particularly strong is in microtransfer printing. And you'll hear a little bit about this today from some of the other speakers. So we're taking high performance indium phosphide PICs, using microtransfer printing techniques with laser coupons, amplifier coupons, and arrays of them going forwards. That gives you a route to printing very high performance chips onto 200 millimeter and above silicon photonics. So this is a particularly important program for JePPIX partners, the INSPIRE program, which is now entering its final phase. And we would hope to see in the coming years availability of these technologies for prototyping and product development. And here you really have the advantage that the indium phosphide components will give you the very good electrical performance, electrical efficiencies for lasers, for modulators, while the silicon nitride will give you that very, very low loss that enables the long delay lines or the super low loss cavities that can really give you the performance in things like lasers. We'll hear a little bit about that later on as well. So we are very much about access to technology. So I'd like to say a few words about how this works once you're developing a product or a prototype. Within the pilot line program of Impulse, of JePPIX pilot line, we're developing a framework for testing chips in software, integrating measurement techniques, and doing virtual testing before we even tape out. So by developing some of the process design kit capabilities and also some of the open standards that we've developed, we're able to create chip description files, measurement description files that give us the assurance that our chips are going to be testable, and not just testable, but also we'll be able to use automated test capabilities. The fab is being aligned very closely, of course, through the process design kits. And with the work we've been doing across the ecosystem, these are now becoming pre-qualified in the sense that if you use a process design kit, you can be increasingly informed, increasingly confident about how statistically significant the data is, the design data is, and you can tailor your designs for manufacturability. So the process maturity develops because more and more of us are using these generic processes. That enables the processes to be run more frequently, building up more statistical data, and we get data-driven design. So Smart Photonics and Fraunhofer Institute already support this way of working, and we're bringing on board other fabs, at the moment 3 5 labs as well. And test, assembly, package is a key part of all this, of course. And if we're going to be moving to many wafer tape outs in pilot phase, we do need to look very carefully at test automation. Our colleagues at Photonics have been developing tools for this, and together with other partners in JePPIX, we're putting in place the libraries, the capabilities, the reference designs, so that we can do all this and plan for it prior to tape out. So this involves reference designs for placing our probes properly, automated part handling so we can work through trays and trays of die identifications so that we know exactly where each die came from on the wafer and can correlate and do data mining. And of course, fiber and probe alignment for fast and statistically significant testing. So these things are all coming on stream very fast now, and we're in a good position, I think, to start the next challenge of hybrid and heterogeneous integration technologies. So a few other technologies that are, of course, very relevant, both from the package perspective, the free space optics, the integration of the package, polymer optics that we could be using, MOEMs, silicon photonics. So we're supporting a program with Photon Hub Europe, which enables these technologies to be combined with a whole range of other semicon and non-semicon technologies. So we can help with the deep tech training. Also, of course, linking people up with investor support and technology support. And perhaps worth noting for European businesses, there is considerable co-finance available for many of these projects. So worth reaching out if that is attractive. So Photon Hub Europe is potentially very valuable to many businesses, not just on the training side, the testing side, the orientation, but also potentially on matchmaking to investors and business coaches and local investment in the region. So do reach out if that's valuable to you. So Photon Hub, very relevant for the early stage prototyping, but also for the upscaling. We're combining multiple technologies. And one thing that we're particularly keen on with the JePPIX approach is that seamless route from our first insights in the technology all the way through the development programs to manufacturing. So particularly important to highlight, these are commercial platforms offering a seamless route to market. So thank you very much. I think that concludes. Ivan.
Okay, thank you very much, Kevin. That's a great keynote and the kickoff of the meeting. So I'm very glad to say that I'm also part of the JePPIX project, because EPIC is one of the partners of this pilot line. And yeah, so with this, I open the Q&A session, because I'm sure you would have questions for Kevin, because as you can see, JePPIX is basically a one-stop shop for everyone who wants to design, produce, and test the chip containing indium phosphide integrated photonics. Maybe I'll start myself with a question of a little bit the outlook of the future of this pilot line and also your other projects related to microtransfer printing. Could you highlight those a little bit?
Yeah, so I mean, this is quite we put quite some effort in with our industry partners into mapping out where we go next. We're in the middle of a road mapping cycle again. We usually set out our vision every couple of years. But we're very much looking towards the hybrid heterogeneous world now. We feel that the underlying technologies have become really quite robust. There are, of course, always challenges in PIC development and procurement, but the underlying technology is now looking very solid. And this is becoming more and more predictable from a technological perspective. So the challenge now is how do we integrate it with more standard semicon flows? Because what we're seeing is a lot of people are looking to integrate at scale. Yeah, they want solutions that they can take out into mass markets. And those of us that are looking at slightly smaller market segments, well, we're quite cost sensitive. So there we need to benefit from process technologies that are really at scale. So there the challenge is really to make all this technology available in foundry processes that are really guaranteed up front. So that's really what we've been working on. The research programs are very much about working out which are the best technological and to some extent commercial strategies for putting together technologies that in the past just really haven't fitted very well together. So we know there's a need, and we're working very hard to make those technologies fit.
Okay, that's great. So I believe Alexander from Alos Semiconductors has a question for you as well.
Yes, thank you very much. Very interesting. In your last comment, you said you're also looking at heterogeneous integration with other silicon technologies. And I saw you also were talking about co-design aspects. How far is that going into the direction of people integrating, for example, optical interconnect? So to address the limitations which we see now with all the artificial intelligence computing coming up and the data transfer being possible on the interposer level and at other stages. How do you see this happening in Europe, actually?
That's an excellent question, and to some extent, well, adding on to in Europe at the end, I think that's quite a signifier. There is clearly a lot of work, corporate work, looking at exactly those problems. Within the JePPIX pilot line, we've been specifically mandated to bring down access to a wide range of players, and therefore we've really focused on generic foundry technologies to make those accessible. But these are very real challenges, the ones that you highlight. How do you get this? How do you get the active components really close into the silicon so that you have performance advantage? From a research perspective, we've been looking at the fundamental reasons for doing it. How much energy do you save? How much bandwidth do you gain? And they are real benefits. I mean, we would not be able to get up to the 100 gig performance on some of our components without a tight integration. So that is important. Once we start getting specific to a market, I think that really has to be developer driven. And so far, the JePPIX platform has very much been trying to open up the technology rather than zoom into a specific application space. So this becomes a lot more commercial than we've been looking at so far. So I think I've sort of opted out of your question.
No, I got an idea. Thanks a lot. I'm curious in terms of what activities actually happening in Europe, because I mean, just also from what JePPIX is looking at, this in a way advantage we may have at least perceived in Europe in the photonic space. This may be a really very significant thing to play out in basically the future of a lot of the semiconductor surface area, large processing units, be it GPUs or CPU, whatever, and the memory, right? And I'm just curious on what is going on there, because we have been asked by some customers using our micro LED technologies to this end. And we are trying to understand a little bit more on where the value chain and in a way partners are in Europe to potentially look at these challenges and supply a little bit more than just technologies, but maybe even some products. Yeah.
Yeah, I mean, a lot of these CHIPS Act conversations that are going on now are triggering these conversations. But as you're probably aware, a lot of the bigger players are outside Europe, but there are players inside Europe, and I think that's organizing now.
Yes, and I think there's opportunities actually, because a lot of these with the heterogeneous integration, right? It opens the door for like you mentioned earlier, for very specialized components to be built and then fulfill very dedicated tasks. And I think this data transfer on the interposer level, yeah, is something which is really facing, maybe not in the next generation, but certainly in the next generation of these applications. And I think there's a clear opportunity with all the know-how we have in Europe to do something there. Yeah.
Thank you. Yes.
Okay. Thanks.
Okay, that's a very exciting discussion, and they will also follow up with a question from Lars Benesch from PSSP. Please, Lars, you can maybe ask it yourself.
Yes, thank you. Yeah, what is the average repeatability of the processes at the moment that can be achieved?
I think that's a tricky question to answer, and you'll never really get it from a fab, I think. The fab will argue that it's design specific. The question is, how much effort have you put into fitting your design to the process? So there is a learning cycle, pilot line phase, if you like, which takes you from first prototype to something that's manufacturable. And that's not new to photonics. That exists in the electronics world. The microelectronics people do it. Now, you might argue that some microelectronics processes are so robust and so well described that it's a fast process. But even there are multiple cycles before you get to manufacturability.
Yeah, of course. And especially with photonics, I mean, this is critical in many different ways. Can you have a percentage once the process is fully up and running and not too complex?
Well, I am not a fab. I'm not a commercial fab or speaking for one. I'm speaking on behalf of quite a few organizations that are offering open access technology. And of course, when you start out, you're starting often from nothing. Your design has not been positioned yet. But it can take some time, yes, and some investments to get to the point where you really understand your design space, and that can take many wafers. And I think that's certainly true of the electronics sector. One thing that slowed us down a little bit, I think, in the photonics community is many people have been starting with the MPWs and hoping that they'll learn enough. But really, if you want to move to product, we need to be moving to working to work with wafer batches to get that learning, to really understand the impact of tolerance on performance.
Yeah, fully agree. Thanks.
Okay. Thanks for the question. And we also have KLA Tencor, one of the key players in the metrology systems in the world, and John Linden has a question, of course, related to metrology for you.
So, hear me okay?
Yes.
Yeah, okay, good. So, yeah, I think maybe this has been leading up to this question, but so within your testing processes, you mentioned, we just talked about this now as well, do you implement any metrology testing other than actual just functional and automation testing?
Well, as an academic, absolutely. Fabs, I think I can speak on their behalf and say absolutely as well. But these are moving targets as customers are looking for more precise yield learning. The metrology requirements go up and up. So it's a continual development.
And this isn't the standard metrology tools and testing that.
Well, it's everything from really getting to grips with the PCMs. How accurately are you etching? How uniform is it across the full wafer? the compositions that are involved, all the way through to relatively simple electrical characterizations and then functional testing, as you mentioned. And I think the big win we're going to have in our community is when we join the dots on all of those in a really effective way for generic products.
Okay. Does that answer your question, John?
More or less.
Okay. Well, also at this point, I should say, please stay everyone until the end of the meeting, because we'll have a little formal discussion at the end, and you a second chance to reach out to our speakers. And maybe just to conclude on this part, I'll ask you, Kevin. So, what's the typical way of reaching out to JePPIX, and whether I need more than just an idea for the design of the photonic integrated chip, or do I need more? And how to reach out to JePPIX, taking into account that there are dozen partners? What's the entry point?
Well, the JePPIX website lists all the partners that are active, and they're all very happy to speak on behalf of the consortium. So if you want a commercial contact, that's out there. Many are on this call. You can also reach out via social media at the LinkedIn channel for JePPIX, or via the email addresses coordinator@jeppix.eu. And depending on what you're looking for, the connections are relatively straightforward, whether it's an orientation, whether it's a training event, whether it's connecting to suppliers. There are many ways that we can support.
Okay, that's clear. Maybe one last minute question from David Cheskis from TriEye. David, would you like to ask it?
Sure, thanks. I think microtransfer printing is a really interesting approach. Just could you comment real quickly and briefly on what kind of devices is it really good for? Actives devices, other types of devices, and what's the status? What needs to be improved on the limitations, and where we're at with that?
I think we have a colleague from X-celeprint on the call that may like to speak to that question later on. But what I would say is that in the Inspire program that we're coordinating ourselves at TUE, together with X-celeprint and IMEC and SMART and other players, we're looking very much at the manufacturability issues. And we think some of those can be really addressed by looking at mode matching control in both the technologies, and being clever on the design. Which opens up an interesting opportunity, I think, because you can start adding in a lot more sophistication into the active elements if you can start bringing in powerful integration technology on the 3.5 side. So that's one area we're looking at. Also looking at how to get more components in a coupon. That could be quite powerful as well for density in the future. But I don't think I can speak to exactly where the commercial challenges may or may not be, but that's where the research challenges are looking now.
Thank you.
Indeed, as Kevin says, you need to stay until the end of this meeting, because we keep the microtransfer printing for the dessert, and the last talk will be done by the X-celeprint. But in the meantime, so I'd like to thank Kevin for this kickoff, and we switch to the second talk that is given by the French giant Thales, and Vincent Billault, the research engineer, will tell us about applications of microtransfer printed 3.5 on silicon nitride for microwave photonics and sensing.
Yes, thank you for your introduction. I hope you can all see my screen. So good afternoon, everyone. My name is Vincent Billault. I'm working at Thales Research and Technology, and today I'm going to present you our recent result of microtransfer printed 3.5 on silicon nitride for microphotonics and sensing applications. So at Thales, we are extremely interested in photonic integrated circuits because the extremely reduced footprint provide high density integration. It provides also new or improved functionalities such as nonlinear photonics, optical phase sensitive circuits, etc. But going to more and more complex PICs, we figured out that we cannot only restrain to one platform, because we need to mix complex element to form a really high dense peaks. For instance, we need lasers and amplifiers that are coming from indium phosphide technology, and also we need low loss propagation such as delay-aligned external cavities. So this come mainly from, in our case, silicon nitride. So in order to really go to high functional complex photonic integrated circuits, we need hybrid integration in order to get the best of different platforms. So that's why we are part of the INSPIRE consortium, which is a program is aiming to establish a world first platform combining low loss waveguides and ENP active. And you have here a scheme of the INSPIRE consortium with the 3-5 part, the silicon nitride part, and the transfer printing. And at Thales Certain Technology, we're the end user, meaning we want to make demonstration to show the strength and the potential of the combination of such a platform for our application. So today I'm going to present you our results about distributed acoustic sensing and the benefits of microtransfer printing 3.5 on silicon nitride for that application. So actually, distributed acoustic sensing relies on relay retrodiffusion of a probe line on an optical fiber. So you send the light on an optical fiber, and each defect returns a small reflection. And by analyzing the amplitude and phase of the backscattered light, you are able to retrieve the strain condition along the fiber, and so to resolve in time and space the acoustic reference. So this application is very well spread in structural health monitoring of building, roads, etc., but also perimeter surveillance, ocean acoustic monitoring, etc. So at TRT, we are using a distributed acoustic sensing with optical frequency domain reflectometry. Just so as a reminder, we with OFDR we are modulating a laser. We're modulating the frequency of the laser linearly in time. So you have on the bottom left a picture of in blue of the frequency of the laser versus time, and we send that chirp waveform on an optical fiber. And when it is reflected at a given position, it returns and it is detected by mixing with an optical with the local oscillator. So a given position returns a bit not a given bit not as a detection. So we are measuring the whole fiber by just looking at the spectra of the output of the balance detection. So this is a principle of detection of interrogation of the optical fiber. And in that case, we also need a reference interferometer to measure and to correct the chirp nonlinearity. Just to give you some insight of the parameter and the key performance of such technology. So actually, one main element in the OFDR is the laser, because the laser line width is impacting the detection sensitivity, and the laser line width determines the maximum length that can be interrogated. And also, one important parameter for the laser is the tunability, because the sensor spatial resolution and the acoustic bandwidth is directly given by the tunability of the laser. So for instance, if we send a wavefront with the shape on the upper right with a linear chirp with bandwidth delta f over a certain time, the spatial resolution that we can interrogate is linked to the span of the frequency modulation. So for 10 gigahertz, we have a resolution about 1 centimeter. And the sensor acoustic bandwidth is linked to the repetition rate of the modulation of the laser. So for instance, 100 microseconds give an acoustic bandwidth of 5 kilohertz. Now, to give you an example of what we can find commercially for this kind of application, you can find like 4 gigahertz span lasers with a 10 kilohertz repetition rate with a 10 kilohertz laser line width. So in order to boost this figure, we need really to go to a low line width laser with an increased frequency bandwidth of tuning. And that's why we went to hybrid integration of ENP on silicon nitride, because we can really benefit from high performance gain sanction coupons, and all of the benefits of silicon nitride with the precise filtering, all the very low loss waveguide, etc. So in the framework of INSPIRE, we design a laser that is aiming to work for distributed acoustic sensing. You have here the design of the laser, so a microtransfer gain section on a passive silicon nitride circuit, which is mainly made of a Sagnac mirror to make the reflection and to close the cavity, and a cascaded micro ring for frequency selection. You have on the bottom right a picture of a chip that is coming from the Inspire, and you see what we have 4 different lasers with different ring sizes, coupling up, etc. Because we wanted to investigate the trade-off between the quality factor of the cavity and the tunability for high-speed tuning. The idea here is to really to link the performances of the acoustic sensing for application to the concrete parameter of the laser. Here are some results of the laser we designed. So we have a fully functional laser in the telecom band, around the 5070, 1580. And we designed specifically the laser to have quality factors around 30,000, 60,000 in order to have kilohertz line width classes, but to still be able to tune very rapidly the frequency of the laser in order to have a high resolution of the acoustic sensing. On the right, you have an example of measurement of the line width of the frequency noise of the laser, and you see that we are in the kilohertz line width class lasers. If you want more information about these results and characterization, I encourage you to see this paper was published in OFC. So then one important parameter is the tunability of the laser. So we looked at the frequency span that we can obtain with our laser with using an external calibration interferometer. So in that case, we put 2 kHz sawtooth modulation on the SOR and on the rings in order to tune the frequency of the laser. And you see here experimental results of the laser. So from 10 GHz on the left to 30 GHz on the right, of instantaneous frequency versus time, which really is higher than what we can have commercially. So in that case, it's the wavefront was a bit nonlinear because of the modulation of the sawtooth modulation. But with the external calibration interferometer, what we did was to pre-distort the wavefront in order to really increase the linearity of the wavefront. In that case, we obtained, for instance, on the right, the instantaneous frequency and the unwrapped instantaneous frequency. We obtained 30 GHz of frequency chirp emitted by the laser with plus minus 1% of residual nonlinearity. So just to get a step further and to link this laser to application, we actually used the Inspire laser to our Thales distributed acoustic sensing setup to benchmark this solution compared to existing other solution. And actually, this distributed acoustic setup is on the right. It is a plaque that is probed with a calibrating sensor with non-mechanical mode. So we're exciting one mechanical mode of the plaque in order that has an optical fiber on it, and the optical fiber is interrogated in order to measure the phase signature of the mode. This is the kind of application, for instance, you can find in monitoring health structure, etc. So this is a scheme of the experiment. You have the Inspire laser here on the top. Here, I mean on the left. On the top, you have nonlinearity correction in order to compensate for the nonlinearity of the chirp. And the bottom of the experiment, we're sending the wavefront to the fiber on the test, and the retro reflections are detected on the IQ demodulator. I won't go too deep into the details of data processing, but this is what we got with Inspire laser and with other lasers that we are looking. So in gray, you have the phase signature, theoretical phase signature of the mode we are interrogating with our acoustic sensor. In blue is the laser we're designing at TRT. In red is a commercial laser. And on the bottom, you have two signature of the phase of the modes that we are measuring with the Inspire laser. And what we can get from this measurement is that the Inspire laser perform as good as our solid-state laser, but is better than the commercial off-the-shelf laser, which is a really good news in our case. And also, it was at a fixed bandwidth, but if we increase the bandwidth of the chirp, we see on the bottom right that we have much more points, meaning that we have a much more higher spatial resolution. And in that case, it overperforms all solutions, commercial and also all other solutions in terms of spatial resolution. So to conclude with this laser, the integration of ENP on silicon nitride allows to have very narrow line width, largely tunable lasers, which can provide millimeter range resolution for acoustic sensing, and it's enabling a new new resolution, new functionalities that we cannot have with other means. Because of the, we also have a laser line width at the engineering, because the process of fabricating silicon nitride and integration are more and more known and reliable. And we have a calibration of the frequency and the frequency modulation wavefront to minimize nonlinearities. I've summarized here the performances of the commercial and the Inspire laser to show that the step forward with the inspired solution that can be done with a heterogeneous integration. And in the future, on future perspective, we want to go to all integrated sensor fiber readout to have the integration of sensor fiber readout on the photonic integrated circuits. So in that case, we will have active components for the laser I just presented, but also balanced photodiode, etc. And also meter range delay line in order to have really the calibration on the chip in order to have a fully functional chip that is for the application. So with that kind of chip, we can have on-chip calibration of the frequency modulation and on-chip demodulation with balanced photodiode. And one thing I didn't have time to talk is the use of microtransfer 3.5 on silicon nitride for microwave photonic circuits. In that case, in the Inspire project, we want to make a frequency shifting loop on a photonic integrated circuit. So here you have on the right here the scheme of the chip. And the idea is that frequency shifting loop can be used for IS-30.
Yeah,
Sorry.
Excuse me. Yeah, we lost your screen sharing a minute ago. So could you come back to share it?
I can. Why did it stop? Okay. So lastly, what we want to do is to have all integrated microphotonic circuits to show the advantages of such platform with really high dense and complex circuits. In that case, frequency shifting loop integrates lasers, meter range delay lines, SOI, frequency shifter, etc. on a set chip. So it's really the heterogeneous integration will allow to have all of the components on the set chip and to reach performance that cannot be reached with other application. So thank you very much, and thank you all of the partners of Inspire that make this lasers and future prospect of possible for this for the frequency for the microphotonics and sensing application for us at Thales.
All right. Thank you very much, Vincent, for presenting this. Incredible developments at Thales. It's a very exciting application of the technologies that many of us are working on. And I mean, as you mentioned several times, it has been done in close collaboration with the JePPIX partners and specifically the Inspire project. So I think the representative of JePPIX, Kevin Williams, would like to ask you a bit on the feedback of working with these technologies and your outlook for these developments. Please, Kevin.
Yeah, no, I would like the opportunity for you to share a few thoughts on some key aspects of this. It feels to me like you're a bit of a front runner with using these hybrid technologies with open foundries. And that's potentially quite challenging. I'm just curious, I mean, why is now the right time to be doing this? And what is that risk to reward balance for you?
Thank you. Actually, that's a very good question, because the idea here is that we cannot we cannot compromise on performances in order to put put the photonic integrated circuits in the on top of the screen, because what we in terms of applications and the current solution we provide, for instance, the concurrence can be tough, and we need to really take the best of the photonic integrated circuits and not limit ourselves to only one platform to go for, because otherwise it won't be as good as it can, as the full potential of photonic integrated circuits. So the strength of hybrid integration is that it can really play with all of these high functional building blocks and really high performance building blocks in order to really outperform our current solution. If I just go back, for instance, to the here to what I do you still see my screen?
No, not at the moment.
Oh.
Oh, sorry. I just yeah. So actually, we for this kind of application, for instance, distributed acoustic sensing, we're also looking at solid state laser solution. And the idea is that photonic integrated circuits can really bring a lot of advantages. For instance, the bandwidth is really great and really interesting, but it has to take the best of the possibilities of the platforms to really to provide this order of magnitude of in terms of spatial resolution for these applications. For other applications, it might be another parameter, but it's really the idea behind this.
Okay, maybe one other quick question for me, if I may. There must be quite a team at Thales behind this, but quite a lot of technologies as well. How do you see the Thales team evolving? How much know-how do you bring inside? How much outsourcing can you do?
Yeah, so well, the idea is like Thales' vision of that aspect is to work with foundries in general. I mean, we are kind of foundry agnostic. But while mastering the design of our device, because we think that an important part of the design performance lies in the ability to understand the applications. So that's what we do at Thales, but also to understand the mechanism behind the foundries, the photonic integrated fabrication. So the idea is to really have the to work with major European foundries to see experimentally the advantages and convenience of different technological platforms for our applications, and to really, for given circuits, to take the best of to a given application, to take the best of what is possible to do with European foundries.
Okay. Ivan, I shouldn't take your time, but thank you for that.
Yeah, this was very, very informative. Maybe anyone in the audience has questions, so please feel free to push the raise hand button, and we pass you the word. So Jeroen Duis.
Yeah, sorry. I was having a question around the volume applications. I think the heterogeneous application is really looking to do high volume production. And I think when we do hybrid lasers right now using edge coupling, it's all driven by performance and lower volume application. So where do you see this landing in the volume landscape?
Not really easy to answer, because I mean, it's always performance is always a key of what we want to challenge when we're talking to our applications. It's always the key figures of the design and the products we're selling, but also the increase in terms of volume is very important in terms of to reduce the cost and to increase to increase the reliability of such a process. So I think it's maybe a trade-off between the high volume capacity and the performances that we can achieve with with the processes. Did I answer to your question, or?
Well, it doesn't provide an answer on like where the volume is for this application.
Where the volume is?
So what is the goal for Thales in the end by participating in this project? and driving the volume.
You mean what is the future volume of such a product in terms of market?
Well, since I understand it from Smart and from X-celeprint and from IMEC, since they're like foundries and equipment builders driving the volume, Thales is in the project as a end user. So you want to scale up the base technology. So where do you see the applications going in the end for Thales?
I mean, we have a lot of applications that surely needs this kind of device. For instance, we master a lot of for acoustic sensing. Just to give you an idea, we have applications of the sea surveillance, perimeter surveillance, etc. And so a lot of the volume of the what can be done is linked to these specific sectors. But we have a lot of sectors. I mean, just only one application. A lot of sectors we are addressing, like also like sectors such as optical communications, microphotonics, etc. A lot of these sectors needs really. I think that photonic integrated circuits can intervene in a lot of this lot of applications. So it's not only it's more than just one application, one product. It's really rethinking what we can do with our product, and in that case, volume will be really. I mean, not an issue in that case because it address a lot of topics in these applications.
Okay, thank you.
Okay, I hope that answers your question. All right, and maybe one more question from our old friend Jörg Smolinski from Nanoscribe. Hey, Jörg.
Hello, everybody. Nice to meet you after the summer. I have a question about, as far as I understood you, the transfer printing is the next step, if I understand, so heterogeneous integration. So do you expect even better performance after that, apart from the miniaturization? What do you expect there?
With the integration of the laser and the
PIC,
like
and
all
PIC
the interrogation, I think the main element of interrogation of optical fiber come from the lasers. So really, this demonstration is a really good start for the integration of distributed acoustic sensor. But the fact is, we need also the performances, and I mean the improvement of the PIC version will be also the integration of the calibration delay line, because we can have in that case an internal calibration of the frequency of the laser, and so we can have a retroaction that is really fast and adapted to the compensation of the nonlinearities in of the laser. So in terms of laser performances, except from the fact that also, of course, we are staying on the chip, so we don't have any coupling losses to go to detection. Except from that, I think the major improvement will come from the internal calibration in order to have a fully packaged all fiber sensor readout.
Mm-hmm. And how do you, I mean, you still will have an optical interface between the micro-printed laser and the PIC. So you're looking at this already, or is this something you're going to explore during the project to optimize the losses and reduce them?
I mean, in terms of optical interfaces, the laser would be it will be the same thing as our current design is a micro-transfer gain section on a silicon nitride passive circuit. And the circuit will be the silicon nitride passive circuit will be then the future large PIC with the calibration delay line, so it will benefit from the gain section, etc. Of course, we will still need optical interfaces to go to the optical fiber, but in that case, we can we're also looking at a way because for the current version it's great in coupler, but with edge coupler we can reduce the insertion loss, etc. So to really improve all of the aspects and of the interfaces between the laser and the other optical elements.
I think we maybe can help if you have issues with the coupling to the fiber. So you can contact me.
That's right. Okay, thank you.
Okay, great. Yeah, this is the spirit of the EPIC meetings. So indeed, I make sure that you guys get in contact. So unfortunately, to follow up on the timing, we need to move on. So we thank again Vincent for presenting the vision of Thales. And the next talk will be given by Smart Photonics, another partner of JePPIX. And Alonso Millan-Mejia, senior scientist and process architect, will talk about putting light into your chips and heterogeneous integration of indium phosphide photonics. Alonso, the floor is yours.
Yeah, 1 second. I need to share. Okay, so is it already?
Yeah, just go full screen. And,
okay, but thank you for the invitation. I think it's a pleasure to share our vision from Smart Photonics. The title is Putting Light into Your Chips, because we have a nice element, the indium phosphide, that allows you to bring light into the other platforms. So, well, I start with, we observe that there are global challenges that require new technologies. Like we see that there is a massive power consumption in data and in telecommunications. There are new sensors that they are being created and they need to be for autonomous mobility. And also we see that the cost of healthcare is increasing. There are also more applications towards getting more on the side of robotics, new sensors. So it's increasing the number of applications in the medical domain. And for that, we believe that the photonics integrated circuit is one way to tackle them. This one consists of the light. So instead of electrons, we use light mostly. And we leverage on the integrated circuit. So it's we put several devices all in one single chip. And we leverage all the semiconductor industry background to get this one. We observe that there are many parallels with electronics. So we observe that now we are getting the same similar figure, that when we have designers, foundry, packaging, integration as different companies. And this allows to use several of the same things as electronics, like the same equipment. We can use the same equipment as electronics, similar economies of the scale and cost down, and also similar margin for tech leaders with volume. And we say we place ourselves in this part of the ecosystem when there are other partners, like some of you are here in this talk, and they are like taking different parts of the other chain. To simplify the life of our customers, we have our process design kit toolbox. We provide it and we leverage with our process know-how and the building block refine that we have been working in already for a decade. And we provide it to the customer so they can get fast prototyping and ready to market in a faster way, reducing learning cycles. I think this is extremely important to reduce the time to market. From our technology, indium phosphide is key to success because it's one material that allows lasers and amplifiers. Our technology is a bottom integration, which has no compromise between active and passive components. So we can have active laser and amplifiers, high-speed modulators, phase or amplitude modulators, and different passives. So a lot of connection waveguides, splitters, combiners, and everything can be on wafer electrical testing. So that's one of the main big advantage. And this allowed low-cost integration circuits. Smart Photonics itself is a European-based foundry in indium phosphide. We are an open foundry and we manufacture indium phosphide wafers for our customers, customer designs. And we have process and capacity to support different customers from prototyping to volume. Based on the production line that we have in-house, or validate PDKs, and we offer the end-to-end service to have a easy access to our technology for new players. Indium phosphide is a solution that can solve a lot of things, but it's not the only one in the photonics ecosystem. And the different platforms have different benefits, as it has been mentioned already in the previous talk. So there are three main platforms: indium phosphide, silicon nitride, and silicon photonics, and each of them has their own strengths. We start with interacting in this hybrid technology in the Inspire project. It's already presented by previous speakers, because Inspire take the best of all the platforms. So by combining them, take the best, and you can have no compromise in performance, which is critical for several applications. So we start learning using the Inspire project how this technology works, what we can do with it. And what we observe is we have a complementary performance. So indium phosphide give you complexity and performance in actives, number of actives, and silicon photonics, in this case silicon nitride, give you low cost and scale. So they are complementary parts of these different domain properties. And but we consider one key factor is it has to be a wafer level integration. This will keep the costs down and will allow to get the fast technology implementation. In the Inspire, we have a technology development with several other partners. We learned the technology, but now we are also part of another consortium, Ambrosia, where we utilize and validated our technology advancement. We also explore more application because it's important to know which other application they can use this technology. In this case, I think there are some medical applications that are being explored here. But this is discovering the technology. What is the next step? So the next step for us is another European project called Photonics Fab. Photonics Fab is a full European-based photonics device value chain, where the main goal is to make an industrialize this technology. So not just demonstrate few applications, but really create a production that you can, as a customer, arrive and already start using the technology. And this is a path to high volume manufacturing. As you can see in this image, there are the different part of the manufacturability is there. So for the design, testing and fabrication, the integration, the packaging, and one of the most important one is the system and application. So we have relevant partners that they have interesting solutions that we want to test the limits of the technology. And some of these applications could drive to high volumes. One of the questions is, what do we need from this community? So what SMART needs from this community? And I think, in my view, is we need applications. So we need that you bring your ideas and we can convert them into products. And this is important because we need a close communication, because it's needed to bring new technologies to the market. We provide the platform, but you deliver the application. So it's how we see it. Some conclusions from my talk. I think integrated photonics, it helps to solve a lot of challenges in large and high growth markets. The industry has many parallels with electronics and is moves towards an horizontal value chain, is what we observe. The high application demands drives the need for platform integration. So application is important, that we get more and more applications. Adoption of integration platform needs close interaction with the photonics ecosystem. We need to talk more with the ecosystem. We need to understand what you want to obtain, what are the limits, so we can get the solution that fits your needs. And we consider indium-based devices plays a key role in integrated photonic value chain. Yeah, that's my thoughts. Any questions?
Yeah, thank you, Alonso. Very informative talk. Yes, please prepare your questions and push the raise hand button. And in the meantime, I'll just ask you, Alonso, to maybe say a few more words about the Photonics Fab, about when it starts, what's the way to communicate to it, how to get your chips done with Photonics Fab.
With Photonics Fab, so it already started. We have some applications already planned, and we are working on it. But we are creating a new PDK. We are creating. We want to get more application in order to start running wafers, because as soon as we start running more wafers, we learn more. We get more maturity on the technology. At this moment, I think you can contact in Smart Photonics Alessia. She's taking the lead on the Photonics Fab from Smart Photonics side, so she can address to the correct people to start the discussion how you can try to use this technology in an early stage.
Okay. Thank you. Anyone else? If not, maybe okay. Wilfred from SUS Micro Optics, please.
Yes, I saw in one of your first slides you mentioned your PDK. So there are some external components in there, like lasers and indium and APDs. What we get quite often from our clients who come with silicon photonics or even with the APDs, they don't know how to optically interconnect those. So how do you see the integration of micro optics in your PDK in general? And this is something I kind of miss in many foundry services. They give people a chip, but then they don't know how to optically interconnect it to the outside world. And so what I think is, and that's what Peter O'Brien is pushing a lot. I mean, he has that always in his talks, like the PDK of the foundries to combine this with the ADKs of the assembly company. So I mean, we met last week with in Bremen. There was a nice FICONTech event. So there were some of the people who are here today were already there a couple of weeks ago, and that was one of the topics. So how do you combine the PDKs of the integrated photonics or silicon photonics or whatever you want to call it, or indium phosphide based photonics with the assembly packaging? So this is definitely something that I'm kind of missing still.
Yeah. Yes. Well, in our PDK, we provide information of how is the light at the facet at the output, but yeah, that how you take that light and put it in your package is something that we leave to the customers to do it, and in general we try to address them by giving them to the packaging partner that can help into how to integrate it to the final packaging.
Yes, this is indeed the current situation, but how can we improve this? So there was a lot of effort in heterogeneous integration. So on the laser side, there has been done a lot, which is great. So there's much better ways now to integrate a laser into silicon photonics or other integrated optics solutions. But how do you see it on the other side? So I've seen mode fields from waveguides that were very difficult to assemble. So they create high assembly constraints to the optics that follow. So, and then on the other hand, there are grading couplers still. The grading couplers have very limited functionality because of their limited bandwidths and output angles and so on. So I think there's still a need for, and maybe Fix or somebody else could, or FICONTech could comment on this. How do you see that
how can we approach this subject? I see a lot on heterogeneous packaging, but I don't see a lot on how to, on a system level or subsystem level. So this is maybe that's not your job, but I see that more and more as an issue for silicon photonics to become more widely used. And
yeah, for hybrid, I think now by putting the active components on top, we have the coupling between the indium phosphide to the silicon photonic, silicon nitride. Something that you don't have to worry much because it's already happening on the chip.
Exactly.
But yeah, from the silicon nitride, silicon photonics towards outside is a good point. Yeah.
Okay. So thank you again, Alonso. To catch up on the timing, we will thank you for your talk again, and I invite the next speaker, who's Andrzej Polatynski from VPI Photonics, and he'll tell us about the single design and multiple fabs modeling and design strategies for hybrid PICs. Please, Andrzej.
Yeah, thank you very much, Ivan, for introduction. So as you mentioned, I will just try to explain you a bit more on how we can really make a design of the hybrid structures. And yeah, partially also touch the question which you already mentioned, not maybe answering the question how such assemblies could be done, but rather how currently people deal with it. So very shortly about our company. So VPI Photonics is the market leader in software and services for photonic design and analysis, with over 25 years experience with regional offices about Europe and North America, global network resellers over the whole world. And we believe in three main aspects in integration. So clearly, we try to integrate efficient simulation techniques and professional design functions for devices, circuits, and systems. Interoperability, which allows you mainly to interface with any third-party simulation, design, programming software, or even lab measurement equipment. And into solutions, which we try to target via joining many different projects, especially here, thanks to the JePPIX that we are here together, and getting much more into the research collaborations to find out the new solutions offered by many different partners, many different foundries, and also solutions provided by them with different materials and platforms. So if we'll just look on the portfolio, I already mentioned we are simulating everything from device level up to the very high link engineering with component design and transmission design in between. You'll find out that we have quite a lot of different products on very different levels, mainly to offer you the possibility to find out the tool which is just necessary for you and use only it without necessarily to go details into all other products. Today, we will mainly focus about the photonic circuit product and the PDK libraries, which are add-ons to the circuit product, allowing you to design hybrid integrated circuits. So very shortly about the workflow when we are simulating. In first place, always whenever we'll be talking about the circuit, there needs to be some waveguide structures which will propagate via the structure. This you can simulate mainly on the device level via just building the cross section and propagate via some basic structures. Then from the structures, when you know how they form, either from the simulation or from measurements of your circuits already, you can build the full circuit design. And of course, further, after the circuit design is created, you can validate the circuit versus the system spec and find out how it behaves in the whole network. I mentioned about the interoperability with the different tools, and here I would like to especially mention toolkits for the foundry-specific components, including some of the ones that were already mentioned, but mainly focusing about already different platforms. So usually one single toolkit focuses on a single platform itself. Then another interface which we believe is critical for making the design is the interface within the simulation and the layout. This is especially needed that whenever you are making the circuit, you want to make sure that you can later on export the layout and fabricate it. And this all together is created within the Foundry PDKs, which provides the information mainly on the circuit level, layout, and all of this is all built into the single library. And finally, of course, if you want to go a bit more further, there is possibility to co-simulate your optical circuit with some electronic design automation, for example, via the Keysight ADS. Okay, so let's jump directly to the process of the design. So whenever you are making design, at the end, what you want to always have is an assembly transceiver. Assembly, for example, here, the transceiver. And what we and foundries are offering you is usually just some kind of library of blocks which allows to connect. So how really this can be done? Firstly, of course, from these components, you build the circuit design. You can clearly see that except of the components in the middle, which are focusing around the PIC taken directly from the library, there are also some additional modules which allows you mainly to extract the characteristic which you wish to perform, which you wish to execute from the simulation. You can clearly optimize your design, simulate fabrication tolerances, try to estimate the yield of your structure. And once you are already sure that the performance is as needed, there is a magic button which mainly allows you to click and exports directly the layout of the structure. Such layout can be directly either further moved and reworked in the layout tool or directly be used to export the GDS file, which can be provided to the foundry for getting the fabrication. Here, all this process which I just shown is based on the Heinrich Hertz Institute polymer PDK. But what is quite interesting to see is that within all these polymer structures, which are purely passive, there are also two active components, which are the indium phosphide actually components, the GAIN and the photodiode. And this is actually one of the first approaches how people make a full design using hybrid integration, just by combining different modules into the single library. And then if you will take a look on the exported layout, you can see that the GDS does not include itself the photodiode, and it does not include your GAIN element. These components are assembled after the fabrication process of the polymer chip is created. And within this first experience, directly the fab takes care that the proper assembly is performed and provides you already the full assembled chip. But how it works with the different foundries and different platforms? Let's take a look on this based on the example of indium phosphide, again, Heinrich Hertz Institute PDK, but this time full indium phosphide, externally modulated laser, and based on the Lyonix foundry, offering the design for silicon nitride based on the optical beam network former. If we'll simply create such designs, usually you will always create single component in indium phosphide foundry, single design for the silicon nitride chip. You will try to simulate. First, you will find out, okay, our indium phosphide laser works as expected. Our silicon nitride chips work as expected. We just export layout of one device, export layout of the other device. And I mean, the very simple process of the design is ready, suitable for any foundry run. There are only two issues. First one is that we are with the two different layouts, so with two different chips at the end, and we need to make sure that the assembly of them works. And that's actually very problematic because we are not able to verify the final performance of such chip, how it will work after the assembly. That's why what is already quite well known with many solutions, you can do very similar design, but within the single schematic, simulate both designs together. So simply we are just having a module at the end, which allows us to build the spot signed converter to ensure that the proper propagation within the indium phosphide chip and silicon nitride chip will work. And you can simulate directly first, of course, the performance of your modulator to ensure it's correct, and then try to look for the performance of your final chip after the silicon nitride. And then very often you will see that it's not necessarily works correctly because of some additional attenuation, because of possibility of getting some noise, because of fabrication tolerances. It might happen that the final chip, even though both chips are working perfectly, is not exactly working together. And of course, within the simulation, there are many different options how you can optimize the design to make sure that the performance is correct afterwards. And of course, again, with the very similar approach, you have magic buttons which are allowing you to export the layout to the given to the desired layout tool, or directly to get the GDS files and provide to the foundry for fabrication. In this case, of course, it's much we are getting single design only, and we are able to optimize our final chip performance and still getting the GDS files which can clearly be fabricated within the fabs. But we are still facing the same issue. We are getting two chips from the two fabs, and we will always struggle here mainly to get the assembly, unless, of course, we will pay somebody to do it for us. What we believe in the future is, and what actually we are starting already to enable for the people, is to take such PDKs or actually create your own list of modules and build custom PDKs. With such custom PDK, you can include mainly any kind of building blocks within it. It can be directly from some foundries. It can be just created by you or by your partners. And you can just define directly the components. And again, there might be based on your expertise, there might be some custom modules, for example, provided by design houses, or just by already existing foundry elements. Of course, there might be some issues. So if we will just take randomly some PDKs, we might find out that some layer names will overlap, and mainly the export will be broken. But if only we will take care that there is no single components which are actually overwriting the same layers, most foundries, when they will fabricate the structures later on, they neglect layers with non-default names defined by them. This means that if we only create some proper mapping within the layer names to make sure that there is no crash between the different foundries, we could generate a single GDS file which could be provided to two different fabs, and they both could fabricate the structure. How it would look like directly on the process, it would be very similar to the already existing solution, but in that case, we will export a single device, a single GDS, and it will allow us, after mainly the optimization, provided directly to the fab, and the fab will deal mainly with the both sections. Of course, it's still problematic because mainly you will still get usually two chips, because none of the foundries will take responsibility of fabrication of the other process. But already you will get closer to the final goal that at some point maybe we could provide a single GDS to some company, and that company could take care of processes for all of them. Of course, there is one main issue here. In order to be sure that this process works, we need some standardization. We need to make sure that the layers are standardized, that they don't overlap, and that the fabrication processes does allow for people to fabricate both chips within both foundries without making the issue that one fabrication can destroy the previous one. So to conclude, what we really need at this moment is a big help in the standardization of photonics. And this includes mainly standardization of everything, starting from very basic data formats, very basic building blocks description, up to high-level descriptions how multiple foundry platform chips could be fabricated together. And where we can help you is mainly into enabling the various strategies for the design, hybrid PIC simulations, optimizations, validation versus device and system performance, helping in building such PDKs and sharing them with all potential customers, and into acceleration of your design via the automated export into the fabrication. So please try to build your PDKs with us, try to talk to us about all possible topics that includes photonic integrated circuits and more. So also in the case you would like to learn more on the co-simulation with electronics, about the layout aware design or optoelectrical co-designs, please talk to us and try to find out some common solutions. And within, I would like to thank you very much, and I'm open to any question.
Okay, thank you, Andrzej. That was very informative. Do we have any questions in the audience? Feel free to raise your hands. In the meantime, I'm wondering a bit if the JePPIX softwares have any trial options.
Yes, so we usually offer the trial versions. So if you are a new customer, you can contact us and try the software for free for 2 weeks with some additional meetings with us where we can help you mainly into finding out how to build your design within that time. Also within the JePPIX platform, we are offering some, I would say, chip licenses just for allowing you to get the access for the foundry runs, for the MPW runs, allowing you mainly to build your design and also get the final GDS exported to the fabs to get the final chips.
Okay, good to know. Good to know. Jörg, your question maybe?
Yes, you have shown very nicely a way to standardization and homogenization of lasers to PIC and these kind of synthesis. Just mentioning a small thing, spot size converter. So that's still a crucial point to do this. How do you define them? Do you have already things in as modules? How could we work together? We are building blocks like this indirectly, as one could say.
Yeah, it's a very good question indeed. Many foundries provide directly the solutions of how to integrate their structures into other platforms. I'm not aware of all the platforms, don't want to give directly the names now, but I'm aware that many platforms, if you just contact them and talk to them, they will tell you how the components should be looking like in order to build such interface. What's more, many of these companies has already such modules created because of some projects, because of some work. And if you just talk to them, usually you get the possibility to use it. And there is many papers showing integration from Heinrich Hertz Institute to the polymer, to the silicon nitride, also between smart and silicon nitride structures. I'm also aware about some interfaces within the lithium niobate platforms and indium phosphide. So many companies already work on such components. Some of them keep the IP, how the building blocks look inside, and does not really explain and show it. Some of them directly will give you the answer and even help you to build such interface if you'll be willing to work with them.
Yeah, with our technology, the 3D printing of the micro optics on the edge of these kind of lasers or chips, we go even a step further. So we can enable optimized use of the, for example, INP area in order not to have too much space for the spot size converter. So I think we maybe should talk together how we can represent this in your modules. That would be very interesting. I think I'll contact you.
Yeah, sure. It would be very interesting to see such possibility as well.
Okay, good. Yeah, thank you, Jörg. And John Linden from KLA.
Yes, hi. Thank you. So I think you touched on this a little bit. I was wondering if you can elaborate a little bit more about what are your main failure modes that you've seen in the designs? You mentioned some noise or different coupling noises. that you notice in the end?
So it's many different effects depending on your application. So if you will be talking about very basic applications of the hybrid integration, where you just interconnect the active elements from indium phosphide and passive elements from any other fab, one of the critical issues will be just the back reflection and directly how it will influence your laser performance. But I mean, whenever you are designing any kind of PIC, it usually needs to operate as in some system. If you build a transmitter, it will be connected to some fiber elements, to some receiver parts afterwards. You need to make sure that all of these effects are taken into account there. And we already noticed within some other design we were doing before that even small misalignments in the fabrication, for example, for MMIs, the imbalance you can get might very heavily affect your final system of some transceiver, which you will never see directly on the circuit level, because just on circuit level you'll see, okay, there is very small only imbalance, but then your whole system, after even some digital signal processing or afterwards, you might find out it will actually destroy the performance of your full system afterwards. So you can account for mainly any physical effect, but it will always depend on the applications you want to target. I mean, if you have anything special in mind and given applications, feel free to contact us, discuss, and we can try to target what exactly issues might be happening there.
So you still see it, at least the state of technology today is that we're still manufacturing the whole components and testing them after, making sure that that they stand up to the standards that you designed them for. So.
Yes, so I'm afraid that we are still mainly currently at the level that even when you want to get the hybrid integration, we usually simulate two separate chips and try to assemble them afterwards and hope everything works. And clearly for now, when the PICs are very small, usually it's still okay, because usually you can quite nicely predict the performance and everything. But I mean, this is not scalable. Whenever you'll be talking about bigger and bigger circuits, more and more components, it will just not work anymore like that.
Thank you.
Okay, if there's no further question, I suggest we thank Andrzej again for the great presentation, and we go for the next speaker. As mentioned, the presentation of FICON-Tech unfortunately did not happen because the speaker could not join us. On the good side, though, we have a sponsor today, and that's a Fix Photonics Assembly. And we have here Jeroen Duys in the room, who will say a few words about your packaging partner, Fix. Just unmute, please.
Thanks for giving me the stage here. And maybe like a few words also responding to what John just requested. It's like when you have two different foundries right now that are making the same circuits, but they're physically two different chips. When we do the packaging, so we take it on the other side, we see that we physically have two different chips with different dimensions that we need to work with, but also the chips, they have different bows, for example. So as a result of like the epi process, you get stress in your materials and you may end up with like wafer bow, and the wafer bow in the end may result into different couplings per waveguide, depending on how we do the assembly. So I think also there's like beyond the simulation tools that are out there right now, there's also a lot of physical effects that we still need to develop. So you really see this hybrid integration is still at its early infancy, and you really need to work closely with the different foundries and the packaging company to come up with a solution. I've been having some slides here about different projects that we have been packaging where you can see we do hybrid integration using edge coupling of 3-5 devices. We do it on top, so wafer level integration and the hybrid integration, as well as the die-to-die bonding. And I think what we are seeing, it really comes down to like the volumes that are driving the markets and the technologies, as well as the stability of your value chain. Like how easy can it be if you do edge coupled integration using SOAs, that you can easily switch one SOA vendor to another SOA vendor, so at least you can build your parts and you can continue to do your delivery. While otherwise, if you have a PIC design and you have one missed delivery, you're completely locked up. So we see a lot of advantages that people are currently exploring by using the end facet coupling of standardized interfaces. So you will see as well that we will come with a ADK pretty soon for the characterization packages. So it's not hybrid integration, but it's really one chip platform at a time that we can do the packaging for. The advantage is if you're adhering to those design rules, the integration of hybrid devices is also going to be very straightforward, since it's just the integration of two different chips, but with a similar interfacing. So I think that would leave me as introduction with FIX, where we do packaging assembly for these different devices. Thank you, Ivan.
Very well done, Jeroen. So yes, please, if you're looking to package your chips, feel free to contact Jeroen or me, and I put you in contact with him. And now that the packaging topic has been open, I'd like to invite the next speaker of the session, Thorsten Meyer, the CEO of Vanguard Automation. We'll talk about the next generation photonic integration and packaging solutions. With photonic wire bonding and facet-attached micro-optical elements. Hello, Thorsten.
All right, hello, can you hear me?
Yes, the floor is yours.
Yeah, you can hear me, you can see my slides. Good. First things first, thank you, PIC and Ivan, for hosting us. It's always good to put up these meetings to network and talk, and also thanks for Natasha for getting us coordinated. My name is Thorsten Meyer. I serve as CEO of Vanguard Automation. I had the pleasure to join 2.5 years ago, also to this industry from the outside, and it's been quite a ride. Our mission, as many of you know, I took a quick peek. I think someone mentioned it. Some of us saw each other at FICOntech, might have heard the topic already a few times. So I think I shall be able to get through this in 10 minutes or perhaps a little longer if you give me. I was kind of actually under the assumption, yes, FICOntech is not there. I have a few more minutes. But anyway, so we obviously, our mission is to sell photonic packaging integration solutions leveraging 3D laser lithography and what we believe is a fairly unique IP portfolio that originated at the Karlsruhe Institute of Technology of photonic wire bonding, but also micro lenses. And I want to talk a little bit more about how we've gone about implementing the technology in a form factor such that we can scale from prototyping to volume production. Quick step back, this is, I think, what brings us all together. I tend to say here, we all know PICs are growing dramatically. I think someone in the beginning mentioned, optical computing and AI will take center stage in a few years here as well. I think that image perhaps is missing, but today we primarily work with tele and data communication. So if you wonder where we spend most of our time on, what drives our R&D roadmap, it comes from that space. And then the next adjacency is really sensing, but in particular FMCW LiDAR. There's quite some interesting applications in quantum, and I also have seen some companies here in the virtual room that use our technology and have put it through the ringer in terms of quantum applications as well. There's been, as we heard here, is considerable progress made. A lot of people tackle this challenge of building systems out of discrete chips. But as we also see, it still remains a technical commercial challenge. Why is that, and why do we think that 3D laser lithography or two-photon polymerization brings some very interesting aspects into solving these? Most of the challenges really arise from two facts. We have to do mode field matching, and the components are all of different material platforms, as these bring the right physical attributes to solve some of the challenges we're trying to go after. Mode field matching today often requires additional micro-optical elements that have to be placed, which prolongs the process. It adds extra cost. You need very high precision assembly in order to couple with very low losses. Depending on where you play, if you look at really scaling this, and this is the big challenge, reproducibility and throughput are big topics. And then obviously, depending on the industry, reliability under various conditions. So if you look at Tele and Datacom is primarily, not only, but primarily damp heat, temperature cycling. If you look at FMCW LiDAR, the temperature range goes up in the automotive industry. And when we talk to quantum people working on quantum applications, it really gets very demanding in terms of close to zero loss, and you have to operate at millikelvin. No wonder that a majority of the cost is not really in the chip itself or the components, but the package. So as I mentioned beforehand, we believe we have developed a fairly universal solution and promising solution leveraging 3D laser lithography. One approach is photonic wire bonding, originally really inspired by electric wire bonding that most of you are familiar with as well. Has been around for a long time. It's very reliable, it's fast. You can have very narrow pitches. The loop control is very tight. And when the team back then set out, this was sort of the inspiration. We need to be able to do what electric wire bonding has been done for semiconductors. We need that for photonics. So you basically 3D print, and we'll talk a little bit more about that. A direct connection between the components to be connected. And as you already can see, it's a freeform structure. You can create, you can taper down from larger mode fields. You can create 3D trajectories, so to compensate things like pick and place offsets and inaccuracies. But also lenses are a very viable approach because lenses integrate nicely into an existing process. They can be printed on wafer or on dice level. And then you can go and pick and place with much looser pick and place tolerances. So how does this, for the sake of time, I want to jump right in. I have a few short videos to give you an idea how this looks and feels if you automate the entire process chain. Maybe quickly before we get started, from a process perspective, you could operate as a wafer. Here, for sake of example, we have an arbitrary assembly, which you could have assembled here. We have an active light source, we have some multiplexing, some modulation, and could go out on a fiber. Yeah, the areas to be connected here will be immersed in a photosensitive material, or resin, as we call it. One important point here for the resin that I might perhaps for this with the time rush forget later on, the materials is a pretty big component of our technology. They have to be specifically designed for things like adhesion, stability, and also reliability under accelerated H-test. Then we have a femtosecond laser. Most of you, I think, have heard enough about two-photon polymerization and are familiar with this. Where we use the same laser to essentially detect the interfaces through scanning that as we use to actually structure the bond. Yeah, and so that gives us very high accuracy in the process, and you don't need to calibrate. So the interface detection happens with any component sub 100 nanometers, but with known components, we can create reliably an accurate interface detection that has an accuracy of 50 nanometers and less. So that is usually very accurate for identifying the mode fields that have to be connected and matched. So once the bond is structured, we need to, and that's an important step for volume production. You also have to automate the process of developing, meaning cleaning, removing the unexposed resist, cleaning the assembly, and then providing an encapsulation. See the video is running here now exactly as stepped on this. So what you see is the automated detection of the assembly, and the objective lens is immersing here in the resin. Yeah, so it's the lens remains immersed in the liquid, And then we do interface detection. Obviously, you can't see anything, nothing is moving. It's the simplicity is almost the beauty. If you now imagine you look through the objective lens, this is roughly what you see. A bit of a shout out to our early partners of Ficontech. Those of you familiar with their technology, you can recognize the resemblance to the process control master. The important for automation and scalability is that you have a software solution. And what you see here is a professional sequencer that allows us to define processes and control those processes, set them up, and automate them. In the middle here, you look through the objective lens. What you see is actually it's a simple chip, has 12 waveguides here exposed on each side that have to be connected. You see some faint line, perhaps, I hope you can, in your image, which are already existing wire bonds. On the right-hand side, we see the interface detection, and it can happen in various ways. The system can recognize marker structures, but it also scans through the chip and can identify the waveguide tip here. And if I run the video, that's exactly what's happened. What will happen, you will see the automated interface detection here. And it will do this from both sides. For the bandwidth here is maybe a little slower than it would run in reality. It's normally a process that runs in 20 seconds max, including writing. It will do that on both sides. And when the interface is detected, you will see a light flash going left to right here. And that's really how long it takes to actually write one bond. And you'll see that that is in a matter of seconds here. So that will happen. I think you can hopefully see that light flash going back and forth. That's a structured bond. If you move forward, you have to automate the entire process of developing, encapsulating. By the way, you encapsulate the bond to provide a different refractive index, so the bond operates in a single-moded manner. It's a little bit like a fiber where you have a core and a cladding around it. So it's a cladding, but it also at the same time provides protection. And you see this tiny assembly here. You can fit in a 12-inch wafer. So all the machines we have are designed for 12-inch wafer operation and automation of the process. If I start this, you'll see that we zoom in a little bit here. And we built first a little dam around the area that has to be cladded. That's so that no cladding is contaminating the rest of the chip or the assembly. Yeah. And this area could now include as much as easily as 80 bonds. So that's quite, we have maybe a millimeter or two here. And so this is not 3D printing here. That's a high precision dispensing and curing process that's fully automated. So when that is done, this is sort of how it looks. It gives you a little bit of a glimpse. We built a dam around the area about the connection here. Here you have in this specific case, a single mode fiber, and you have a PIC. It's dammed and it's cladded and it's fully packaged at this point. So one thing that's very important if you come with a new coupling technology is we're trying to really build, which became apparent quite a bit at the beginning when we interacted with our first industry customers. You get all kinds of chips thrown at you, all kinds of things. There's very little standards, and you find yourself doing a lot of repetitive work. So we're really seeking to build an ecosystem not only of people who can offer services around the technology, but also try to work with foundries and component makers, if you will. And here's just some recent examples. We work quite a bit with AMF in Singapore, where now if we get an AMF chip, we've designed a coupler together with them. It's something very simple. It's a very simple structure. We don't need anything sophisticated because the technology lends itself to adopting as it uses the freeform structure. And we can repeatedly, those are not the lowest losses. So you can easily, you can go sub 1 dB in terms of loss, but those are the loss figures we can produce repetitively, reliably, over and over with very, very high yield. So working closely with AMF, here on the right-hand side, you should see silicon nitride with AIM. It's a little covered here on my slide. Very recently, we coupled to a laser from Mentec, with about 1.5 dB loss reliably across a larger batch of lasers. And so the team here is very eager currently reaching out and working with component manufacturer so that you can say, hey, if you work with this chip, you work with this coupling technology, we can show you yields, we can show you losses, this is repeatable, and it's, you know what you get, basically. A very important point is, so if you look at two-photon polarization, there's two critical questions that I would been asked. Can you do this fast enough? And then will this be reliable? Yeah, well, it's in the product under accelerated aging test. Will it survive in the long term? And as I mentioned, a lot of this is up to the material, and a big chunk of our resources is dedicated to material development. So we routinely do DAMP testing, 85 Celsius, 85 humidity, and also temperature cycling. If we had more time, we could speak a little bit about our industry. Customers do actually a lot more. Sumitomo released a paper at OFC that's available, in which they talk about how they've qualified the technology for their telecom transceiver modules. Maybe in conclusion, as far as the technology itself concerned, there are quite a bit of benefits. You can create low loss connections to arbitrary remote fields of many material platforms. So you have, if you will, it's a bit of a soldering iron for PICs. It's a very universally usable approach. Two-photon polarization is very automatable. The core technology has been around for a while, so the yields are usually very high. You usually have not the problem that there is a lens or a bond missing after you print it. It comes more down to your materials. Will they be reliable over time? There is both methods significantly relates pick and place tolerances. The bond, the interfaces of the chips to be connected when we create a bond are always identified. So the bond itself can easily compensate pick and place tolerances of 20 to 30 micron. That's what we sort of provide as a standard. They can do more, but that would require some NRE to ensure that's really working. Reliable connections under various conditions. By the way, on the topic of lenses, with the lenses, you expand the mode field, and that also gives you the ability to probably pick and place. It depends a little bit what you couple, with what loss you couple, and so forth. But lenses may bring down the pick and place tolerances or requirements to 5 micron. Yeah, that's something you can do in a much more relaxed, passive way versus active way. You can realize very high interconnect density. So you see down there, it's some results that this is working. This is not a photoshopped image, where we take a multi-core fiber, and essentially we take the lower fiber and say this core connects to core N here, connects to core Y on the other side, and the software can do the routing. And this method really gives you ability to have a very viable coupling method between multi-core fibers. Specifically in the context of AI applications, we have had multiple discussions where companies or engineers ask us, hey, how would you go about a pitch of 20 micron on a chip? And then how do you connect that to fiber? Common fiber arrays, that doesn't work so well anymore. So multi-core fiber is definitely an interesting route here. And the method itself, since the bond is a very thin structure, lends itself to very narrow pitches. This is sort of how the platform looks today. There's 2 machines. So we developed the technology, but we're a product company. So we sell machine software, the materials, as well as a standard product and services around the product platform. Important to take away is that there's a machine for the lithography process and a machine that completely automates the pre and post processing. Those are standard machines. They're software defined, if you will. So the fabrication process is defined and configured in software. And we enable our customers, so we can provide standard processes and do this. We always provide a solution, but we also enable our customers or ecosystem partners through a development system to adopt fabrication processes to their own requirements and needs. If you have a change in component, you want to prototype a new system, this is something that is then software defined rather defined through the hardware setup. Then this is underbuilt here by standard fabrication processes that come with the system that can be adopted to your specifics. And as I mentioned, we develop and sell the materials and provide product and services around it, specifically our development support to enable customers and service partners to be successful with the technology. In summary, it's one platform that supports various types of connections, if you will, or coupling methods, photonic wire bonding, micro-optical elements. These are detectors that have been printed on. Here's a lens that operate, have been tested under close to millikelvin conditions. And also we have some technology that allows you to write larger structures. Usually the right field of a high resolution lens dictates the size of the micro-optical element that you can print, but we have technology that allows you to stitch-free print larger structures as well. And in closing, looking at the watch, a quick shout out to some of our industry research and also service partners that are out there. I think few of them are in the call. I saw Freedom Photonics represented, and I think also folks from Canada working with C2MI. Maybe a point here, we're keen on and looking for service partners that can provide services on the technology, as well as to interface with foundries and component makers, so we can look how we can couple well to your components. And with that, I close my session and I would be open for questions. I don't hear anything.
Oh, sorry. Yeah, okay. I'm saying, yeah, this was the cutting edge packaging solutions for you provided by Vanguard. Thank you, Thorsten. Okay, yeah, for the sake of saving time, I will only take 2 questions. So please, yeah, John Linden from KLA.
Yes, hi, thank you. Quick question. So are you doing this fabrication? Are you seeing this done as well as in embedded glass interconnects in silicon, indium phosphide as well? The 2-photon process?
Can you do me a favor, repeat the question? I don't know whether I acoustically understood.
Sorry, can you hear me okay?
Yeah.
Better? Okay. Are you doing this 2-photon polymerization also within silicon or in indium phosphide other than just in glass or photoresist?
Oh, you mean whether we structure direct connections in other materials? Yeah. That's a very good question. We've received that a few times, and to be perfectly honest, I'm the wrong guy to answer it. It's not a standard we would offer as a standard solution today. I think it's 3D laser lithography. Theoretically, the lithography machine could do some of this, but I'm not one of the scientists here. I'm the wrong person to give you credit. It's nothing we do today as an offering. Let's put it out that way.
Thank you.
Yeah. So the materials are essentially polymer materials that are designed by us with the application requirements in mind.
So depending on different wavelengths or what you're aiming at, that would be different materials.
We primarily most of what we do is in the telecom FMCW range, but we have room to go up to. So some of our customers and research partners have used the technology and up to 2K nano. Yeah. The material itself can operate down to 500 and I would have to look up the exact number. Yeah. And there's a little bit of a difference between lenses and bonds. The bonds, if the bandwidth the wavelengths goes down too much, they will not be single moded anymore. So you can still transfer light, but it won't be single moded. And the lenses are fine to operate at lower wavelengths as well.
Okay, thank you.
Yeah.
And the last question from Alexei from University of Latvia.
Yes, thank you. What were the temperature? How fast did the temperature change on those temperature tests? It was 3 degrees per minute or higher, lower than that?
Very good question. I will, if you send me an email or Ivan helps me, I will answer the question.
Okay.
I'm not 100% sure how exactly the temperature cycling test was done.
Okay, understood. Okay, fine. Of course, there are very standard procedures all across the photonics, but it's actually tricky question. Yeah, it depends on the industry.
Okay. Well, so thank you, Thorsten, again for the great presentation. And last but not least, we'll hear from the X-celeprint. Ruggero, supply chain scientist, will talk about the microtransfer printing for integrated photonics.
Yes, thanks for the introduction, Ivan. I'm trying to share my slides. Can you see them?
Just go full screen and you're good to go.
I will go full screen if I can access them. 1 second. I'm not able to access the bar. Okay, now yes. All right. So thanks for the introduction. It's a pleasure to be here and to talk about microtransfer printing for integrated photonics to such a wider audience.
1 second, Ruggero,
yes.
Because we see your presenter screen. You need to change to the. If you go on the top. Then top left, you can change the screen that you're sharing with us.
Is that working now?
Yeah.
Okay.
You're good to go.
Yeah, thanks very much. So I'll give a short company introduction. So the core technology at X-celeprint is microtransfer printing, which is a wafer scale compatible pick and place technology that allows to transfer micro components on different substrates by exploiting viscoelastic property of the PDMS material. Our business model is a licensing of the technology itself, but we also provide side services like development of microtransfer printing solutions for specific applications or microtransfer printing prototyping services. We have 2 main sites. That quarter is in Cork, Tyndall National Institute. We have our labs in there. We have access to the clean room facilities, and we have a microtransfer printing tool for prototyping, research, and production in there. And our subsidiary is based in Micros Center, Research Triangle Park, Durham, North Carolina. We also have access to clean room facilities and microtransfer printing tool in there. Actually, our sister company, X Display, which is dealing with the display part of microtransfer printing, is also taking care of the development of prototyping microtransfer printing tools. Just to give you a quick overview on X-celeprint numbers to understand.
Ruggero?
Yes.
Sorry again. Yeah, I was wrong. We still see your presenter mode.
Oh, let me stop sharing and sharing. Now.
Full screen.
Sorry about that. You see full screen?
No. Just push F5.
Yeah, it did. Not sure why it's not working. Let me try doing something. I exit the full screen, which was open in the second screen I have here. Okay. So now I'll try share again the screen and see what happens.
Yeah, that's okay. In the meantime, I'll just mention, so now we're coming to the end of our meeting, but please feel free to stay in the room. The virtual room will be open for a little bit longer, so we can have a less formal discussion afterwards, also in more privacy. So we will not be sharing this.
Can you see the slides now?
On YouTube. Yeah, this is still presenter mode. Just go at the top of the window. You can there select which screen you're sharing. You can click on one of those. Yes, this one or one next to it. Next to it, is there another one?
Mm-hmm.
Another menu? Somehow we don't fully see the screen.
Okay, so I'll try to disconnect the second monitor. Let's see if this works now. Now it should work. See that now?
Yeah, that's good.
Yeah. Yes. So just to give you a few numbers about X-celeprint, we have 720 plus patents, more than 100 millions in development, 18 years of commercial development, 85 customers funded projects, today 200 plus man years of experience, and 20 plus printers, transfer printing tools sparse worldwide. So how microtransfer printing work? Basically, you choose the layout of the PIC, and then you create a source wafer with usually with 3-5 components and with a layout which matches the layout on the target substrate. Then you need to release the devices from the original wafer by adding a sacrificial layer at the bottom of the epi. Then you create, you pattern the PDMS stamp with a layout that matches the source, but also the target wafer. And then you can integrate in a scalable way arrays of components on the target substrate. The nice thing, you can mix and match different materials and do that in parallel. Usually after integration by microtransfer printing, you need to interconnect electrically your devices. The alignment ensures any optical coupling between the device that you integrated and the substrate and the waveguides in the substrate. So here just want to give you an overview, a visual overview of the microtransfer printing process at work. So here we have the stamp that goes in contact on the source wafer, pattern with pre-released coupons, and it aligns them on the target substrate through alignment marks and pattern recognition. And then the PDMS is peeled slowly off the chips, and the chips are released. As you can see on the right-hand graph, peeling off the stamp slowly, the adhesion between stamp and top of the coupon is pretty low. Is low enough for the coupons adhesion to the substrate to win and leave the coupons attached to the substrate, and so on. And the cycle repeats, integrating multiple coupons. Here we're focusing on a couple of devices which are part of a 20 by 28 array of 40 micron by 40 micron size, and the material is gas. So moving forward, I like to focus on why using microtransfer printing. I like to divide the advantages or features of transfer printing in 3 main groups. Regarding the starting wafer, we can accommodate very highly dense arrays of components on the source wafer, which allows saving a lot of material, especially with 3.5, which is expensive. You can also completely prefabricate your devices on the 3.5 wafer and pre-test them and integrate only non-good die, if you like that approach. And so that benefits the process in terms of wafer exploitation, and integration. In terms of transferring, the process is highly scalable, as you can integrate arrays of components, which increase the throughput. And you can also mix and match different materials, devices that might have different heights, and create your final substrate in a very flexible way. In terms of printing, we work with passive alignment, as I shown earlier, which exploit alignment marks and pattern recognition. And we can reach 0.5 micron 3 sigma alignment for arrays. We're working at the moment to bring this below 0.1 micron. And at the moment, we demonstrate single post microtransfer printing with 0.1, but we want to use the same technique to reach to transfer print arrays of components. In terms of benefits, high throughput and enablement of PICs. Basically, if you want to create PICs, you need a very tight alignment, both with edge coupling, edge light coupling configuration and evanescent light coupling configuration, if you want to have low losses while transferring the light from the 3.5 to the silicon photonics. So here are a few examples of what we've done with microtransfer printing in integrated photonics. 3.5, where microtransfer printing on silicon photonic or photonic substrates as operational devices or just as coupons of bare material. We transfer them as single post. We demonstrate also array transfer printing for this type of devices. Type of substrates where we print were silicon, silicon dioxide, glass, gallium arsenide, indium phosphide, just to name a few of them. And we also transfer printed on real PICs based on SOI or silicon nitride or silicon nitride substrate waveguide. And we transfer print the components either at the top of the substrate, on top of the boron oxide, on top of the substrate, and also we're able to print inside recess, which might be a plus in case you want to planarize or get a really flat surface at the end of the process. That might be useful for interconnects or to stack other layers above the PIC. In terms of interfaces, we usually print with adhesive layers. We do that with Intervia or BCD. We recently demonstrated that these layers can be as thin as 5 nanometers, which when you go below 30 nanometer, the thermal impact on the device is really low. Also on heating device, highly heating devices like laser. And we also transfer printed without adhesives on engineered layers. There might be metal, there might be dielectric underneath. Usually there are more constraints in terms of flatness and roughness, but that's the way it works. You just need to work around that. And there are a few demonstrations of that as well. So the light coupling configurations that we explore with microtransfer printing for integrated photonics are edge coupling, evanescent, and grating coupling on chip. So this is pretty interesting to make compact your PIC or to explore compact integration approaches like co-package optics. So here another few examples. Indium phosphide laser edge coupled to a polymer waveguide and then to silicon photonics waveguide. Here we have the light that comes out at the other end of the waveguide. We also demonstrate in the Caladan project, EU project, the integration of integrated circuits on a silicon photonic interposer. We also demonstrate recently interconnection to it, electrical interconnection to it. The next is to directly connect the ICs to the optical devices to drive them or to receive signals and translate them in electrical signal again. Photodiodes, we also create interconnection between LED and photodiodes and polymer waveguides. We integrate pixels and PV cells for out-of-the-plane light connection. Well, moving forward in general, we working in a good number of EU projects. It's about 10 between projects where we are directly involved and projects where our partners don't need our help anymore. And so this is actually a strong point for us. We want our partners to be independent, to be able to work with NTP without much support. Actually, some of our partners are expert in the field at the moment. And so they're trying to explore new solutions and bring transfer printing to new applications. So in general, and also we have about 20 customer active projects that I cannot obviously mention here, but that's what it is. So what we're trying to do at this stage, which is also one of the main activities at X-celeprint, is to start leverage on this ecosystem that is growing up, on this sub-ecosystem like the Photonics Fab project that was mentioned earlier, which will bring NTP into production for indium phosphide and silicon nitride, possibly expanding to other platforms. And so in order to do that, we're working in supporting the supply chain, our partners. Why is that? Because we want to accelerate use of microtransfer printing into production. The path to production we expect is to move from prototype to pilot volume to high volume. So we want also leverage on actual EU pilot line for that. And most of that, we want to be ready before the PICs market starts to really ramp up. We expect that to happen in the next 2-3 years, maybe 5 at full speed. And so we want to be ready. And we think it's very important at the moment to work on TRL. So basically, we individuated, say, 7 main areas of the supply chain, which is 3 components, substrates, MTPs, printing sites, thin-film interconnect, design, packaging, equipment, etc. So what we notice is that the TRL is not the same for each partner and in each area. So what we need to do there is to bring the TRL to production level, like I'm talking about 8 or 9 for all the partners and for all the areas of the supply chain. So another important point that was mentioned earlier today in the meeting is standardization, which we believe is a very important point. We're working together with our partners and with Europractice to start increasing standardization. We see that again as a very important point. Another important thing is to create demonstrators to show the capabilities of transfer printing, especially because most of the projects we have closer to the market are with private customers. So we need to have demos that display the capabilities public. And so we're trying to leverage again on our academic partners or pilot line partners to display that public. Another important thing we see is to work on PDKs with our partners, especially to make sure these PDKs match to each other. And another important point for us is these PDKs have to match with all the different areas of the integrated photonics. I'm thinking about packaging. Packaging put a lot of constraints in the final, in the way you do the PIC. So you can have the best PIC, but if you finally not able to put it in a package, then you lose time and then you waste resources, etc. So we want to make sure that all the partners that are working with microtransfer printing are talking to each other, are building PDKs that are compatible on the MTP part, obviously. That's the part that is of interest to us. And that's it. So the supply chain is, at the moment, we classified about 70 suppliers along the different areas of the supply chain. We're obviously focusing on the hardware at the moment, which is 3-fiber IC components and silicon photonic substrate, but slowly we're starting to add more to the other areas of the supply chain, as they're gonna be vital as we move forward. So in conclusion, NTP is a key enabling technology for integrated photonics. It's showing to be a real game changer in the field with all these partners approaching microtransfer printing. We have multiple licensees that are moving into commercialization, and we hope to have the first high volume product out at the end of 24 or maximum beginning of 25. The main areas of application that we are trying to give priority are obviously datacom, and then we are also interested in medical and other niche areas that we're working on at the moment. So that's it from my end. And probably one of the questions was, actually before closing, one of the questions was what can you do for the audience, for the companies in the audience? Well, I show microtransfer printing of a wide range of possibilities, and we're here to help and support with that. What the companies you work with can do for X-celeprint or microtransfer printing. So I think that the actual partners, we need to work together as much as possible to increase TRL as soon as possible if we want to reach the market sooner than later. And with new customers or suppliers, partners that we might work with, we need them to jump on board now, because microtransfer printing is ramping up, and you don't want to lose this chance. I think it's a really real game changer, as I said, and we're open to discussion and to take questions from here. Thanks very much.
Okay, thank you, Ruggero. This is a really key enabling technology, so it was very curious to see it in operation, especially in your video. We have already some questions. Alyosha Shu from Photonics Foundry.
Hi, yes, can you hear me?
Yes, nice and clear.
Good. So it's a rather boring question with respect to what cool things you have shown. I was just catched by an image on slide number 3.
Slide number 3, I can go back there. Now should be easier. Yeah.
And it's basically the question about how did you electrically connect the device to the frame. It looked like spray coated or ink jetted.
Yeah, it can be different ways. I mean, one of the most common ways to do post-printing interconnects is to use a standard RDL redistribution line approach. That's the way we do it. But there are different ways. You might like to planarize with a BCB layer, then open vias and access the electrical pads that you might have on your device. I can show you actually something here. Like, for example, you can see all these devices have metal pads for connection, at the top. And then you can bring the electrical connection. Like, for example, in the case of the ICs, we have a BCB layer which creates a slope around the coupon and brings the electrical connection from the top pads to the metal tracks at the bottom. It depends on the thickness of the coupon, if you print it at the top, inside a recess, etc. Hope that answered the question.
Yeah, thank you very much.
All right. Any more questions? Because if not, I think, we're unfortunately largely over the time limit already. So I'd like to just thank Ruggero for a nice talk again, and as well as all the other speakers of today's session. So we're coming to the end. We will keep the room open for another few minutes just to have an informal discussion and to exchange the contacts between each other. You now also have the standard poll for questions to give us some feedback. So please feel free to fill it in. And I will just quickly share a little bit of the information for you as well.
Yeah, I mean, I think somebody was asking about limitations of microtransfer printing to the market. Maybe the question is limitation to the market. As I mentioned, I'm just trying to answer that, Ivan. I think that, so in order to transfer the process into production, we've seen also in the Inspire project, was mentioned earlier, that there have been some delays in having the process in the production line. But we're taking processes from R&D level, we're putting them in a production line with a lot of constraints. So that's where we need to work on a technical side, but we're in a good spot with Smart at the moment, and we are in a better spot with other customers as well. But usually that's one of the things. That's why I was saying, if you're interested in using this technology, jump on board as soon as possible, because the development might take 1 year, especially if there are no prior development on the prototype at the prototyping level or at the R&D level.
Yeah, that's clear. That's a good call
for
everyone. Okay, thank you, Ruggero. So this was the EPIC Online Technology meeting on hybrid photonic integration for you. And just to mention a few things. So this was presented to you thanks to the whole